Hi, and welcome back. Another piece of lab kit to go through, and today it's going to be the signal generator. Okay. Now, signal generators, they're called those because they generate various signals. Okay. Simple. They do what they say. They come in different varieties. But they all output sine waves and square waves and triangular waves, and if you're lucky they produce other waves. Depends on what type and how much you want to pay for a signal generator. They can also output different modulated frequencies. They can do other things as well. They can output DC if you want. Okay. They can even output waveforms which you can program into them, and they're called arbitrary waveform generators. Still a signal generator. Other people like to call them function generators, and that's what we're going to run through today. Okay, they produce time varying waveforms across a whole frequency range. Okay, normally they're up into the megahertz. More expensive ones can go up into the gigahertz and hundreds of megs and gigahertz. Okay, and the more you pay for them, generally speaking, the wider the frequency range and the more functions that they've got. But bear in mind, if you do buy a cheap one, they're not that good. Okay, so you do want to spend a little bit of money. Yep. That's enough of that. Okay, they produce time varying waveforms, primarily AC and square. Well, no, square isn't really an AC waveform. Okay, if you try and view a square wave using AC coupled on an oscilloscope, you won't actually see a square wave. Okay, because a square wave is actually a flat line that you turn on and off. Okay, it's a DC essentially, but it's still time varying. Now then, the functions of a signal generator, how to use them. Well, down on my desk here, yet again, I have got some more toys for you to look at. So, here's our function generator, or signal generator if you like. Okay, that's this little box here. Now I've also got my oscilloscope set up here. Okay, I'm only going to show you really the screen of this one because we're not really too interested in learning about the scope. I've already done that. So that's just there to actually view our AC waveform, okay, which this little baby here is going to generate. Now it looks quite complicated. There's lots of BNC sockets down the bottom for various outputs and inputs, and it's got a hell of a lot of controls on the front, but I'll take you through the bare bones, take you through the basics of it, and that will more or less cover you and get you up and running on nearly every single generator that you come across. And I'll leave you to play about with the other functions on it as and when if you use a different one, you'll probably have some of the same functions as the basic ones, which I'll run through. They'll all do exactly the same thing. They might be in a different position. Instead of a pushy button, they might be a twiddly knob. Who knows? Okay, but a signal generator is a signal generator. At the end of the day, there's not really that much difference between them, except for looks. Just like your oscilloscope, they've all got the same twisty-turny knobs, just in very different positions. Okay, so a signal generator outputs various functions. Okay, and by function I mean a particular wave. So we've got up the top here, this is our control for changing the actual shape of the wave function. Okay, so we've got a sine wave, triangular wave, square or logic. Okay, push it once, you got square, push it again, you've got a logic function. I'll show you that later on. And the bottom one's DC. Okay, nice flat line. Okay, DC is time varying just like everything else. The only difference is it's a constant value, it doesn't oscillate. Further down, the other major controls are, we've got range. Okay, that range is used to push the decimal point up and down the scale on the screen. You can change it for well, you use the range function in conjunction with this twiddly turny knob here. Okay, and by moving the decimal point up and down and by adjusting the rotary knob, you can actually adjust various values on the screen and shift the points backwards and forwards. That's mainly controlled to use the range function is used under the frequency setting. So down here, if we press frequency, you change the range and twiddle the knob, you can change the frequency. The other ones is the amplitude, that's the other important one. Okay, hit the amplitude, you can only use the centre knob. Okay, and that will vary your amplitude, that's actually written here. So here we got frequency and units. Here we got our voltage, okay, our peak to peak voltage. At the moment this is set to high and low. We want a sine wave, so you can see it's gone to sine wave. Say amplitude, so this is our peak to peak amplitude here. Twiddly knob changes the amplitude, frequency, twiddly knob changes frequency, okay. Duty cycle changes your on and off time, your period for your doesn't change the it does change the period. It's the ratio of how on and how off your say your square wave is, okay. In terms of sine wave, it's the rise and fall of your rising edge, your falling edge of your AC waveform. The same with a triangular, so you can turn a triangular essentially from a triangle into a ramp shape. So they're the basic controls. Down here we've got our knobs. The main knob which you'll probably use is the main output. That's why it's called an output. The other one that you might use is the TTL output. Sweep, I'll come across later on, that's another output. So if you want to sweep through a range of frequencies, okay, so instead of turning the knob, you can get the machine to actually cover a whole range. So it's a bit like you're shifting the waveform automatically. You're changing the period automatically between two values. You're sweeping the frequencies. And the other knob at the end, that's your frequency external. Okay, and that's a frequency input. So that's if you want to trigger the scope, trigger the signal generator. Okay, so you can get it to trigger on various waveforms and so forth and so on. That's not really used. Okay, there are many signal generators, but it's a knob which isn't used that much. When you first start using a signal generator, the sweep output and the frequency external, or sometimes this is called a VCF, voltage controlled frequency. Okay, they're not used when under the basics. I'm not really going to cover them too. I might cover the sweep one later on, but not the frequency. I'll let you play about with that one. So, if you want to get an output, what do? Well, you hook up your output to an oscilloscope. Okay. Best practice is always use a T-piece on your signal generator output. Okay, that way you can feed. Basically, a T-piece is a way of splitting a BNC into two BNC sockets. Okay. Why would you want to do that? Well, to view the output of our signal generator. Double check everything, okay? Because this voltage value will fluctuate. Okay. It says it's 1.7 volts peak to peak, but depending on the impedance of your circuit, this could actually this may not be 1.7 when it comes out of here, and I'll tell you why in a bit. Okay, now first of all we'll run through the basics, and then I'll tell you all about why you have to be careful with your voltage values and why we do actually measure. So in this instance we connect up our BNC probe to our oscilloscope, and that's all we need to do. So let's see what we got. If we want, say, let's take a stop off the top of my head, 10 kHz waveform, 10 kHz sine wave with a say 5 volts peak to peak. How do we set that up? Well, first of all, frequency, hit the frequency button, change the range. This is on kilohertz, so we can either cycle it up, okay, and keep on turning the knob loads and loads of times to get to 10 kilohertz, or you can hit the range button and it will move the decimal point up from kilohertz into 10 kilohertz, and you can use the knob to vary the frequency again. Okay, so you could think of this as course control, going up in tens in steps of multiple steps, okay, and you can use the dial as your fine control. Okay, so I wanted 10 kilohertz, so there we go, that's 10 kilohertz, and we want 5 volts peak to peak, so we hit our amplitude button, and we can change our level here, which is our peak to peak, our peak to peak voltage, and magnitude to say 5 volts peak to peak. And then we have it, a sine wave of 10 kilohertz, 5 volts peak to peak. Okay, sine 10 kilohertz, 5 volts. If we wanted a triangular wave, then we would do triangular wave, set the voltage and the frequency exactly the same. Okay, now then, let's view it on my scope. Now, why can't I see that on my scope? Ooh, look at that. I've got myself a dodgy cable. Look at that now. I'm twisting it around here, we're losing it and finding it. Right, let's go and replace this cable, and you can see that on the oscilloscope screen, okay, what I was doing. I'll be back in a moment. Okay, back again. I've got my brand new BNC cable. Let's plug it into the scope, and we've got gathering into our output, and lo and behold, here we go, we've got our sine wave. Right then, so okay, what we have, 10 kilohertz sine wave. As I was saying before, pressing the amplitude, okay, we can reduce it, so you can see it reducing on the scope, okay, and we can increase it, whoopie-doo, okay. So that's how you adjust your amplitude, or your peak-to-peak value, okay. Frequency is a measure of our period, how many cycles, how many periodic cycles there are in a second, okay. It's a measure of that. So if we hit the frequency button going up the range, you can see that on the scope screen, you see we've got loads of waves, so wave, and varying the knob, you can do the fine control. Okay, so this is actually varying the frequency. You can see on the screen that's varying the frequency. As I said, you've got other functions which come out of a signal generator. You've got your triangular, there we go, triangular wave, logic, or square. We've got our square wave there. For logic, press it again. Logic, as we know, goes between 0 and 1. Okay, it doesn't go negative. We press this, okay, it's going positive and negative. First of all, for the square, for logic square, goes between 0 and a positive, okay. And at the moment, my high is 5.6 volts and my low is 0. And using the high and low buttons, if I press logic high, I can vary that. Okay, so let's set that to say 5 volts for TTL, and the logic low of 0 for TTL. So 5 volts is logic high, 0 volts is logic low, and I can change the low value by hitting the low button, and I can change the low value. You can see it there on the screen. I'm moving my the bottom of my sine wave up and down, variable. So always useful if you're doing any triggering and things like that. You can always simulate, or any logic, you can see where your logic low in your system is. You know what does your 74 LS00 whatever or not. So what is that? That's a NAND gate. what's the off time, what's the on voltage, what's the off voltage. You can play about your voltage levels, see what it actually sees as a logic low. It may not be 0, it may be anywhere from 0 to, I don't know, 1 volt, maybe 0 to 0.1 volt. Same with the on time. Okay, always useful that when you're working with especially CMOS. Okay, depending on what your power rails are set to on your CMOS, it will have various it will determine its high and lows. Test it with that, and if you are working with CMOS, say 9 volts, you can set your logic high to 9 volts. Okay, or if it's low power, you can set it to say 3.3 volts. Seems that we're in power saving nowadays. A lot of digital is done around 3.3 volts. Some of it's even lower. So that's logic. Okay, and frequency is done in much the same way. Okay, for all these amplitude levels are all the same. So once you learn how to drive one of these functions, it follows on through every single one. Okay. Right then, so the other one that I wanted to, the other function on here, the other basic function, okay, is offset. Okay, and offset, this is actually adding a DC value onto your sine wave. Okay, so a normal natural sine wave oscillates around 0, as we know. Okay, but sometimes we want to put an offset onto our sine wave. I mean, for example, a BJT, a transistor. Okay, it turns on at 0.7 volts. Okay, above 0.7 volts. Well, sine wave goes negative, so it's not going to turn on when it goes negative. So you might want to shift it up, so that if we have a sine wave on the base, you might want to bias it with a DC value. And you can do that from the signal generator. So instead of doing the biasing circuit for your BJT, you can simulate that by adding in an offset onto your sine wave, and we can do that by, there we go, we can shift our sine wave up and move our sine wave down. Okay, that's with by adding on either a positive or a negative DC value, and the DC value is here. Normally this is set to 0 because we want all our waves around 0. Sine wave oscillates around 0. It doesn't oscillate around 5 volts or 0 volts, it oscillates around 0. That's what offset does. And it's the same for all the other functions as well. Okay, done. So that's our DC offset sorted out. Okay, and what's next? Well, let's put this back to 0. Our triangle wave. We'll plug in a 1 kilohertz waveform, let's say, of say 5 volts peak to peak. So let's get this reset up. So sine wave of 1 kilohertz. Frequency. Okay, and we go to 1 kilohertz, offset of around 0, amplitude, say, I don't know, let's say make it 5 volts again. Okay, so we've got this all set up for a basic 1 kilohertz signal. Okay, and you can see it on the scope there quite clearly. Now then, the last function on here, okay, another way to alter your wave, and that's duty cycle. It's called duty here. So we'll press that, and this is control. This value is displayed here. This 50% VAR duty. Okay, so it's 50%. So it's on time and off time are equal. So we've got our swings going positive and negative. Okay, they're equal. What happens if we change it? Well, we actually change the percentage of the on and off times. Okay, so it starts to change our waveform. So it is 80% duty cycle at the moment. So it is on for, so it rises here 20%, and it takes 80% of the time to fall. So this is really down to our period. So you need to convert this into a period. of our waveform, and then take the percentage, and that's our rise and fall times. Normally that's set to 50%, so it's equal, as you can see there. We've got nice equal swings, but you'll see that more apparent on the square wave. Okay, and this is a good way if you're trying to simulate a pulsive modulated signal. Okay, where you're varying the on and off times. So you hit duty, and then you can vary the pulse width. Okay, either from 20% on to so you got 20% off to 20% off, and that's your duty cycle. Okay, it's your effectively it's what's called the mark to space ratio. Okay, it's the ratio of the spaces. Okay, the mark to the space. That's really the signal generator functions covered. Done. Now then, down to this internal impedance. Okay, that I was saying earlier. Impedances of your circuit do matter, and we'll do that on the whiteboard. Okay, here I am again. Impedance of your signal generator. Okay, now we've got our signal generator. I'm going to do a symbol for that. Okay, we've got our signal generator here. Okay, the voltage that you measure and the frequency that you set is set across here. Okay, so this is your VPP, your peak to peak voltage, your frequency, your duty cycle, your offset, and so forth is all set across your supply internally, but okay, in series with your supply is a 50 ohm impedance. Very important. Okay, what you actually read is across here, not across the terminals. Okay, and the other thing that I have to point out, which I didn't mention to you, is the actual negative side. Okay, is connected to ground. Okay, be very careful. Okay, this actually connects to ground on the negative side. Okay, so this is in actual fact 0 volts. It's not negative. It doesn't swing positive to this one and then negative to this one. It's actually 0. It goes positive and negative just on your output here. Okay, very important. But this 50 ohms is extremely important in your circuit. Okay, and it does have an effect on the voltage that you see. Now, if you set this to 5 volts here, open circuit, open, nothing connected, 5 volts here, you'll see 5 volts here. Alright, back again. Don't just love when you get interruptions in the middle of a video. Anyway, what I was saying, you got 5 volts on the input, okay, because it's open circuit, we're seeing 5 volts on the output, okay, obvious. But when you attach a circuit onto the end, okay, what will you see? Well, what you're actually going to be measuring on the oscilloscope isn't this voltage, because it's the internal one, August 15th, so you're measuring across here. Okay, so what you'll effectively got is you've got a impedance here. Okay, you've got a resistance of the circuit that you attached to your signal generator. So your signal generator here. Okay, and it's in series with your 50 ohms internal impedance. Okay, you think so? Well, why have the internal impedance? Well, internal impedance is everywhere. It's on your power supply. It's in batteries. It's in these, and these are actually set to 50 ohms. Okay, you do get other ones. You can have high impedances, low impedance ones, but generally 50 ohms is the de facto standard nowadays. And what happens is, with this, you have to be particularly careful, so you get your potential across your circuit, but you also get potential across your 50 ohms. It's a voltage divider effectively. Okay. Now, if this was, say, at a 1 mega ohm input impedance, okay, all the power that you see 5 volts here, 50 ohms series of 1 mega, you get all your 5 volts drops across here. Okay, no problems. If it's greater than 50 ohms by, I don't know, 10 times, it doesn't really make much difference. Okay, but if you have a very low impedance, let's take 50 ohms, you've got 50 ohms in series with 50 ohms. Okay, what's going to happen? Well, this 5 volts is going to split. You're going to dump part of it here, 2.5 volts internally, and you'll only get 2.5 volts applied to your circuit. Okay, that's a big problem. But on the signal generator display, it will still be displayed as 5 volts. It won't change because it's 5 volts set internally. So it's still generating 5 volts, but it's dropped some internally. Okay, and that's one reason why we measure our outputs. Now, it's all very well and good saying that yeah, you get some voltage drops internally, but the lower and lower you take this down, the more power that you drops internally. Okay, can be a problem, can be a dangerous problem. Okay, because how much power can you actually drop internally into a unit? They're not designed to have large voltages dumped internally. Okay, do that to a battery, it gets very hot and it's prone to explode. Okay, I've seen batteries explode before, older ones. Newer ones, there are fail-safes in them, but PP3 batteries, they're particularly nasty. Okay, I have actually seen those in my lab where someone's got hold of a PP3 battery before. They shorted it out, all that power, okay, that 9 volts, okay, and all that current flows. It's very low because it's got shorted out accidentally on a cable clip, and all that power is dumped inside across this very small internal impedance. Yeah, consequently made the battery swell up and it started fizzing really bad. And luckily it was venting, slowly venting. But if it didn't have the vents, okay, it would eventually go off bang. So that's exactly what happens internally to your signal generator. It can only take so much internally. Okay, now some signal generators have things like current limits, power limits, and power monitors, things like that, to actually stop it from generating too much power and dropping it internally across its internal load. Other ones don't, the cheap ones don't, and quite a few of the expensive ones don't either. Okay, because they expect you to know what's going on inside their machines. What will happen is, if this is very low, a short circuit, say, I don't know, 1 ohm, you get 5 volts dumped inside across this 50 ohms. Okay, you've got P equals IV, okay, got a huge current, all the voltage dumped inside, loads of power. Okay, and if you saw my little guide on the DC power supply, you saw the resistors getting fried. Okay, well that's what happens inside here. This 50 ohm load will, well, 50 ohm internal impedance will actually fry, it will start smoking. Okay, and I've had cases with some old equipment that I used to have, okay, where some of these did get shorted out and had smoke coming out of the back of the units. Okay, and when I opened up the units, repaired the damage, okay, they actually caught fire and they did a huge amount of internal damage, so there's a lot of work to rework, but I did manage to get them up and running. Okay, these ones can catch fire if you're not too careful. Okay, and in the cheaper units, when there's no protection, big problem. Okay, because they're only, I don't know, 1 watt resistors, 2 watt resistors. In some units, they're just resistances. So bear that in mind, and that's why we monitor our output voltage. So if you're monitoring your output and you do see it swing to almost nothing at the output, you know something desperately going wrong. It's still generating this power internally in the unit, it's still on, still producing power, you're getting nothing out. You should say, so emergency, disconnect it straight away, check your unit. Okay, that's all I'm going to say on these. Okay, like with every piece of lab kit, the more you play with it, the more use you get to it, the more used to it you get, and the easier it becomes. So just get a scope, put it on the output, play about with controls, and see how you get on.